Grammar is a four tuple, and once you are asked to construct the grammar for some given language, it means we need to construct the production rules of the grammar. Production rules is denoted by P here, and for generating the production rules, you need to keep some non-terminals, and you must have the terminals. Terminals means you must have the alphabet. Using that alphabet, you are going to construct the sentences of the language. S is the start symbol here. So any construction of any sentence will begin from the non-terminal S. So this is important to know. So see how we can construct the grammar for the given language. If you are given some language like double A, double A, double A, double B, double B, double A, and double B, double B. See, this is very simple language, and if somebody asks you that, okay, construct the grammar for this language. So how you can construct the grammar for the language L1. So how you are going to construct the grammar? So whenever you are asked to construct the grammar for the given language, means you need to see the sentences of the language, and your grammar must be able to generate all such sentences. And only these sentences, not other sentences. So you need to construct the grammar rules so that your grammar must generate the sentences that are in the language 1 and no other sentences being generated. Then you can say that, okay, this is the grammar for the language. So means you need to determine some particular structure of these sentences. So how you can determine the structure of the sentences? Means you can describe the structure with the help of production rules. So see, there is no unique way to construct the grammar for the given language. You need to see the sentences, and you have to carefully observe the sentences, what are the sentences in the given language, and accordingly you have to form the production rules. And there is no unique method available for the construction of the language, construction of the grammar for the given language. And in fact, for a given language, you might have many possible grammars. There is no unique grammars. You have many grammars for the given language. So see, for this simple language L1, if you consider this language, then we can write the grammar in different ways. Say I am writing the grammar, say G1 for this language. So once you write the grammar for the G1 for the language L1, you need to describe the production rules like this. And I have already told you that your construction of sentences, your sentence must be generated starting from the start symbol, start non-terminal. So I may write like this. This is the production. S derives AA means double A, double A. S derives double A, double B. S derives BB and AA, and S derives double B, double B. Now see, you have the four sentences in the language, and here you have written the grammars, and it is, you have the V, where you have only one non-terminal S here, and you have the sigma, and sigma includes its symbols A and B, and these are the P. So you have the production rules. So you have the four production rules, and this is the I told you that construction of any sentence must be started from the S. So if you want to generate this sentence, then your grammar should generate. So you can start from the start symbol, this, and you have the derivation rules that directly derives double A, double A. And since this is the string of only terminals, you don't have any variables, so this is the sentence, and this is the sentence you have formed starting from the start symbol. So this is the valid sentence. Again, if you go for this sentence, double A, double B, then you can follow these rules. If you go for double B, double A, you can follow these rules. And if you want to generate double B, double B, you can follow this rule. So what is the difficulty in this grammar? This is the grammar. This is also a grammar for this language. Why this is the grammar? Because I have told you that if this is the grammar for the language, then your grammar must generate all sentences of the language and no other than these sentences. So say you have the language generated by the grammar G1. So language generated by the grammar G1 actually precisely L1. You can't generate any other sentences, those are not in the language L1. So this is the language. So you can say that for any grammar, for any given grammar, you have the unique language. You have unique language for any grammar. So whenever you say this is the grammar for this language, it means your grammar must generate all the sentences of the language, and it only generates the sentences, no other sentences must be generated. So language generated by the grammar is unique. So language represented by the grammar G1 is L1. So you can say that, okay, this is the grammar for this language. Now you can see that if you form the production rules like this, and this is very simple, and in this case you don't require to see any property hidden in these sentences. You just use the start symbol as, and S derives first sentence, S derives second sentence, S derives third one, and fourth one, like this. But difficulty in this kind of grammar is that you have only here you have 4 sentences, so it is very easy to form 4 production rules. But if some language contains infinite sentences, then how you can write the production rules like this? S derives first sentence, S derives second, third, and so on. So this is not the appropriate grammar for this language. So you can write, people can think some more efficient grammar for this language. So see, somebody may say that the grammar for the given language L1 can be written like this, like G1. So I may write G2 here. So G2, you can write for the G2, you can see that you have the S, which is the start symbol, and I may write here A and B. And you know that I have written capital A, capital B means as A, B, these are the variables. So as A and B all belongs to the variables, means non-terminal symbol. So this is the first production rules. Now you have to see how you can replace A. So you can write the production rules for the A, and you are going to replace A because you see that your sentence can begin with double A, means double A, and double. So you have the sentences. You see that you have the even number of symbols. So double A here. The first part is double A, and you can see that first can also be double B. So you write that A can be either double A or E can be double B. Similarly, for the next half, you can see B can also generate double A. So B can be replaced with double A, and B can also be replaced with double B. Now you have the production rules like this. And you can say this is more efficient way to write the rules as compared to the G1. Now, if G2 is the grammar for the language L1, then your G2 must generate the same language. So language represented by the G2 must be L1, and you need to verify. So how you can say that this is the grammar for the language L1? If this is the grammar for the language L1, then you can start construction of the sentences. You can start forming the sentences, and starting from the S, this is the start symbol. First, you have to go for this rules. Now, you need to replace the non-terminals. So next you can go like you have the A. Now you think that how you can replace the A. So one by one, you need to replace. So now here A can be replaced with double A, or A can be replaced with double B. If somebody asks you that, okay, construct this first sentence of the language. So as you see that in the derivation rules, A can be double A and double B. So you need to generate the double A. So you must go for these rules. But see how computer would know whether it should go for the double A or it should go for the double B. So there is no way to tell the computer. Only it can apply the rules one by one. So it may happen that computer can apply the rules first double B and so on. For the non-terminal B also it can apply any one rules, and later on you wanted to generate the double A double B, and it verifies that okay, this is not the string, so your computer will again go for the next options. So next option may be, it may see that okay, I have to go for this rules, A can be replaced with double A. So in the next time your computer may find A can be double A. Now you have the non-terminals B also. So for the case of the non-terminal B, you can again have two situations, and computer can opt these rules one by one. Computer can go for double B first, and it finds that okay, I wanted to generate the double A double A, but this is not the sentence, so it can go for the next choice double A. So here, if it is going to make the correct choice, then non-terminal B can be replaced with double A, and this was the target string you wanted to generate. So in this string you have the terminal symbols only. Terminal means all such belongs to the, this belongs to the sigma star, means this sentence is in the sigma star, means every symbol in this string is taken from the symbol from the sigma. So this is the string you have formed, and since you have started from the S, so this is the valid string. And in short, you can say that starting from the S and using the grammar rules G2, you are able to find double A double A. So similarly, you have found the first string, and you can verify whether it can be generated. Second string can also be generated or not. Third can also be generated or not, and fourth can also be generated or not. And also you need to verify, is there any other strings that can be generated by this grammar? If yes, then this is not the grammar for the language L1. So here you clearly know that grammar G2 can generate only these 4 sentences. Hence G2 is also the grammar for the language L1. Okay. So see, this is the next grammar possible for this language. Somebody may say that okay, I can write in different way. Somebody may try to write the different way for the same language. So we can go for the grammar G3 for the same language. So how can we write the grammar rules some more efficient way? And you find that okay, you have the start symbol as can again be replaced with AB. So now here we have used the two non-terminals A and B, and here A generates AA, and A can generates either AA or BB. B can also generate either AA or BB. So we don't require actually to take some different symbols. So simply you can say double A here. So S derives capital A means the same non-terminals, and you can say A derives either AA or BB. And see, you have only this rules in this grammar, And this grammar is more efficient as compared with this grammar because you have used less number of non-terminals. You have only one and two non-terminals you have used, and you have few production rules, and one, two, and three. And here you see that you have more non-terminals and you have used more production rules. So this is more efficient grammar as compared with G1. So now next you need to verify whether this is the grammar for the L1 or not. So you can find the strings one by one, and let us see how the language is represented by the grammar G3. So again you can verify. So start from the start symbol, and you see that A can replace with A or A can replace with BB. So you can find AA or BB. You can find these sentences, and A can be replaced with BB. So you have the sentence B and B, and again next part can be AA or BB. So this grammar G3 also going to generate the same language L1. Now see, for this simple language, for this simple language, we have the grammar, and three different grammar you have written. So okay, and some you can also write some more modifications in this grammar. You can write in your own way also. So question is that which grammar you need to consider. So there are for a given language that may have the infinite sentences, you will find that many possible grammars for that language is there. So among all possible grammars, actually, we need to consider the grammar that should be smallest and should be consistent with the given examples. So how you can see the grammar is smallest means if grammar has less production rules as possible, and it should use the less number of non-terminals. So our target is not to generate the grammar for the given language. Our target is to find the grammar that should be the smallest one. And this is the difficulty. And this is the kind of optimization problem. And once you see for the optimization, then any problems becomes difficult. So obtaining a grammar for the given language is not very difficult task, but obtaining a grammar that is the smallest one, and your grammar must generate the all sentences of that language, and it is not going to generate any other sentences, and it should be consistent with the given example. So if your grammar has the smallest number of non-terminals or smallest number possible number of rules you have found, then you can say that okay, this is the grammar I am interested. So it is among the many possible grammars, maybe infinite possibilities, we need to consider the grammar that should be the efficient. And this is the hard problem in computer science. Obtaining the grammar of a given language that should be the smallest one is a very difficult task in the computer science. So it's not a very simple task to find the grammar for the given language. So whenever you have the grammar, say G, then we will say that the grammar represents some language, or you may say language generated by the grammar. So how you can define the language generated by the grammar? It is the set of string x which is taken from the sigma star, such that you have to start from the start symbols s, and using the rules of grammar G. So using the rules of grammar G, there is a way to find the string x. So this you can define like this. If you are given a grammar, so language represented by the grammar G can be defined like this. It is the set of string x which is taken from the sigma star. Sigma is the alphabet of the language, such that starting from the start symbol, this must be the S. and this is the start symbol. Starting from the start symbol, you are able to find the X by using the production rules of the grammar G. And here star means you can directly from S you can obtain this, or by making the sequence of production rules here and with the using the grammar rules G. So if you are using the grammar rules in the sequence of grammar rules starting from the S, and if you are able to find this string, then X will be in the language of grammar G. So this is the definition of the language represented by any grammar. So now see, we can see some different example. Like you have the L2. See how many sentences are there in this language. You have the many possibilities, and you can list some sentences here. Like I can be greater than or equal to 1. If I is equal to 1, then you will have A double B. If I is equal to 2, then you will have double A and 4 times B. So you have the 4 times B. If I is equal to 3, you will have A3 and you will have here B6. Similarly, if you have I is equal to 4, then you have A4 and here you have the B8 like this. So these are the sentences being generated by of this grammar. So how many sentences are there? You have the infinite sentences. And you can see that if you write S derives A double B, S derives double A, double B, double B, S derives 3 times A, 6 times B. So this is not the efficient grammar for this language. So now you need to know what should be the grammar for efficient grammar for this language, and how you can find the efficient grammar for this language. And again, I'm telling you that there is no unique way, or there is no programs that you can use for finding the efficient grammars. It will come by your experience. What you need to do is you have to see the relationship on the strings in the grammar. So you can see the properties of the strings of the language here. Like here A, then you will have the double B. So whatever number of A's is there, you will have the double number of B's. So number of B's in this language, if you consider every strings, then you find that number of B's in every strings in this language is twice as compared with the number of A's. And all A must be before the all number of B's. So this is the unique property of this language you have seen. And by observing such property, you need to construct the grammar. So how you can construct the grammar for this language? For constructing the grammar, it means you need to define the production rules. So what kind of production rules you need to have? So whenever you write the production rules, you must have the start symbol. I have the start symbol as, and they see simple way to write here is S derives A, S and double B. And I can say S derives A double B. That's all. There are two rules in this grammar. And how you can verify this grammar generates, the language generated by the grammar G is precisely the L2. How can you verify? So you can see what is the smallest string in this language, A double B. If you want to generate this string, then you can follow these rules. And if you want to generate this string, then how you can form? So you can start from the S. Since you need more number of A's, so you have two times two number of A's you need. So you have to start with the production A derives AS double B. Then since you need only two number of A's, so and that's all. So you can follow next this rules. So A can be S derives A, and S can be replaced with this production rules. So you will have A double B, and next you have double B. So you have four number of B's and here two number of A's. So four number of B's and two number of A's. This is the second string. If you want to find the string A3B6, then you have to apply this rules two times and you need to apply this rules one time, and you will be able to find the sentence A3B3. If you want to go for the A4, then you have to apply the rules S derives AS double B how many times? If you want to go for A4, then three times you have to apply these rules, and now in the fourth time you have to apply S derives A double B. So in this way you are going to obtain all possible sentences of this language only using these two rules. So this is the efficient grammar for this language. This is the grammar which use only one non-terminus here, and that is only S. And you have the two production rules. P consists of two production rules. And sigma here, sigma you know that A and B. These are the terminal symbols. This is the sigma. So this is the grammar for this language. So sometimes even you have the infinite sentence in the language, you should not mean that you have very complex grammar. You may have very simple grammar. So you have to carefully examine the relationship on the sentences, and using the relationship, and you can try to figure out the grammar. So again, I am telling you that finding the grammar for the unknown language is a very difficult task. So here, this is the grammar G which generates the L2. Okay. Now you can go for some more grammar. So let us see. This is the second example of the language. You can see third example now. So I may write L3 is the set of X which belongs to AB clean star such that X is equal to XR. So this is the language, and you know AB clean star means actually I have sigma for example, and here you have the two symbols in the sigma. Once you say sigma star, it means you are telling that AB clean star. So this is the notion. And I have already told you that XR means reverse of X. So X is equal to XR, and this is the language of palindrome. So this is the palindrome property you are going to satisfy. So you need to obtain the grammar L3, grammar for the L3, and here also how many sentences in this language? You have the many possible sentences that can satisfy this property. So how can you write the grammar for this language? So you need to list some sentences in this language. So you will have some more idea. So you have to satisfy the rules X should be equal to XR. And X belongs to AB clean star. And you know that once you have the sigma star or AB clean star, then what are the sentences here? You must, because star can have any values 0, 1, 2, 3, 4, 5 and so on. So once you have AB0, it means you are having the null string. If 1 is here, then you will have the A and B, and like this means this will denote all possible strings of length 0, length 1, and length 2, length 3, length 4, length 5, length 6, and so on. So here, since x belongs to AB clean star, it means here you have the null string also. And you have to see whether the null string can satisfy this property. Yes, you have the null string. You can read from left to right or right to left. There is no change in this case. It remains the null string. So null string will be in this language. Now you have the string of length 1. Yes, this also satisfy this property. Reading from left to right or right to left is same. Next word can be B. Reading from left to right, right to left is B. Next you can go, say for example, double A is also possible. Reading from left to right or right to left is remains same. You can have ABA is also in this language. Read from left to right and then come from right to left. The word is remains same. So and so on. So you have listed some sentences of this language, and on listing some sentences, you might have idea about the structure of the sentences, and that actually you need to reflect in your grammar. So how can you write the grammar for the language L3? This is the some simple target you have. So for obtaining the grammar for any language, what you need to do, you have to find out the non-terminals, and you have to use the non-terminals in the production rules. So simply, actually, you need to find the production rules of this language, and you have to designate some non-terminals as the start symbol. So while writing the grammar for this language, I can use the start symbol, means start non-terminal as S. Now you have to write the rules for this replacement of the S. So how you can replace the S means you have to write the production rules for the S. So say what S can generate. S can generate null string, okay, or S can generate A. S can generate also B. So these are the very trivial cases. S can generate null, S can generate A, S can generate B. So others, for getting the others strings, you can have S can generate. See, if first symbol is A, then last must also be A, because reading from left to right and right to left should be same. So if first symbol is A, then last symbol must also be A. So whenever you are writing the production rules here, you must observe that if you are starting from the A, then you should have the corresponds to A, you should also have the A at the last. And now the problems remain same. So once you write for the S here, again you have to consider the same thing. So other possibility is, if S starts from the B, then last must also be B. And then problem is remains same as here also. Once you replace the S in this rules or in this rules, then again you have to consider, if S starts from the A, then last must also be A. If S starts with B, last must also be B. And then if you want to generate only A, then you can replace S with null, so you are getting only A. If you want to generate BB, then S can be replaced with null and you are getting the BB. If you want to generate ABA, so you have to follow this rules. S can generate A as A. Now you are going to obtain AA, and then S can be replaced with these rules. So these are the rules for the grammars that generates the language of palindrome. So this is, and next you need to list all possible sentences generated by the grammar G, and this is precisely the language L3. Now take some different example, that may be the more complex example you may find. So this is the example 4 here, L4. One thing before going to this example, one thing I need to mention you. If you have sigma and you have sigma A and B, okay. So we have mentioned the sigma star, and you know the notion of this sigma star means this is the set which contains all possible strings of length 0, length 1, length 2, and so on. But if I write sigma plus, if I go for the sigma plus, so the difference of sigma plus and sigma star is that in sigma plus you don't have the null string. So null string is not there. Sigma plus denotes all possible strings of length 1, length 2, length 3, and so on. So this is the only difference. So whenever I am going to write sigma plus, you mean that in this set you don't have the null string. Whenever I write sigma star, it means null can also be there in this set. So this is the only difference. So sometimes you will find the symbol plus, which is known as the sigma plus, and here you have the sigma star, means this is the clean star, which is we say that sigma star, or this is also known as the clean closure. So this is the difference. So if you go for the grammar L4, language L4, then I will say that L4 contains the strings x, which is taken from the set sigma plus. And here, whenever I say sigma plus, means this set does not contain the null string. And next, I want to mention some condition here. So L4 is the set of string x which is taken from the sigma plus, such that the number of a's in x is a multiple of 3. Are you getting this thing? L4 is the language. It contains all sentences x which is taken from the sigma plus, such that number of a's in x. So you have the number of a's in x is a multiple of 3. What do you mean by the multiple of 3? So if you write multiple of 3 means what? 3 into 0, 3 into 1, or 3 into 2 means 6. So this is the multiple of 3. So either a should be either 0 number of a's, or sorry, here 3. So a must be either 0 number, or you must have the 3 times, or you must have the 6 number of a's, or you must have the next multiple 9, and so on. So if a is there, then you have to ensure that the number of a's in x is a multiple of 3. This you need to ensure. And we need to construct the grammar. And again, this is the language that contains many possible strings, infinite possible strings. So how you can obtain the grammar for this language that satisfies this property? So what are the strings in this language? You can list some string. Say if I am going to list, say I am writing B. This is the smallest possible string in this language. Why it is B? Because condition says that the number of A's in X is a multiple of 3. So number of A's in X is a multiple of 3. Here you have only the string sentence B, and how many number of A's? You have 0. So this means here this is the valid string of this language. Then you can have double B also. This is also valid. Number of A's is multiple of 3, and so on. You can have triple B. This is also valid string. Means any possible strings that contains only the symbol B is a valid string in this language. So either you have the length 1, 2, 3, 4, 5, 6, and so on. But once you have the A, you must ensure that it must be multiple of 3. So you can say, if you have the B here, if you have A, then you can have, this is also, so you have must have the 3 times, either 0 times or 3 times, or it's a multiple. And this is the valid string. B triple A is the valid string. Or B A B A, this is also a valid string. B A B A B A B, this is also a valid string. You can have, because the multiple of, now you can also have 3 number of A's, B A B A and A. This is also a valid string because the number of A's in this string is a multiple of 3. So see, your grammar should generate all such strings. So how you can write grammar for this language? So that it should generate the only these strings, no other than these. And hence then you can say that, okay, this is the grammar for the language L4. So what properties you have seen here? Either sentence contains B only, not no zero, no, sorry, no A, or your sentence contains A in the multiple of 3. So you have 3 times or 6 times, 9 times, like the things. And there is no particular order. A can come before the B or A can come after the B. There is no restriction in this case. Only you need to remember that the number of A's in this language, any sentence of this language having the multiple number of A, which is the multiple of 3. So number of A's in X is a multiple of 3. You need to observe. So how you can write the grammar for this language? So you have the grammar. We need to write the grammar for the language L4. So how to ensure that your grammar rules should generate this kind of string? Only B's. And you know that generation of any sentence of your language must begin with the special non-terminals, and which is the start symbol. So S, you have to write the rules for the S. So S can derive B. S can derive B. So you will find the single B here. Okay. Now, how you can obtain double B or triple B or 4 times B? How you can observe? So you can make the repetition. So you can say that either B or BS. So if you want more number of B's, then you have to apply this rules repeatedly. And once you want to terminate, then finally you can replace this S with the rules S derives B. So in you can obtain all possible such strings. So you can obtain the string B, you can obtain double B, triple B, and so on. Now, this is the simple for these cases. Now the question is that how you can obtain such strings, how you can obtain this such string. So what you have seen here, you have seen that if s, you have written the rules s derives b, means s starts with the symbol b, then the problem is actually remains same, because once you have the b you don't require to worry, but once you have the a you have to ensure that the number of a's must be the multiple of 3. So whenever your sentence starts from the b, then the problem remains same. That's why I have written the s, means you have to specify how to replace the s. So this is the recursive way. If you can see, this is the recursive way. S derives bs. So why I have written the s same? Because the at this place the your problem is remains same, because we are not bothering about the b, we are bothering about the whenever you have the a, then you should be more conscious, and you have to be careful to ensure that the number of a's in a s should be multiple of 3. So that's why whenever your sentence starts with B, you should not worry about this. The next for the next cases, the problem is remains same. Now, instead of this, if S starts with A, now the C. Now problem is different. So whatever the string is here, whatever you have the string in this part, it must ensure that the number of a's in total is a multiple of 3. So this is not the same problem here. So how many a's you need? The multiple of 3 minus 1, because you have already used 1. So you can say that I can use the non-terminus a. So s derives a. Now you have to specify for the a. So how you can replace the a? So for the case of a, again you have the same problem. A can starts with b. If a starts with b, then the problem remains same. You need to find out the number of a's in this a, which is the multiple of 3 minus 1, because 1 already have used. So if s starts from a, then this is the different problem, and for denoting the different problem you have used the non-terminals, different non-terminals other than s. So this is the a. Now you need to find out what kind of replacement should be there for the a. So a derives b, it starts with b, then again the problem remains same. Now if you have a starts with a, now how many a's you have? 1 and 2 already have. So here the problem will become different, because whatever number of a's here must be the multiple of 3 minus 2, because 2 you have used here. So this is the next problem, and I am denote by the writing the different non-terminals b. Now you have to specify the rules for the b. How you can replace b? So again b can start with b, and if it starts with b, then the problem remains same. We need again same number of a's here. Now next, if b can be replaced, if b starts with a. So if b starts with b, no problem. If b starts with a, then what happen? Now your multiple completes, one multiple complete. You have first a is here, then you have the next a, and this is the third one. So now one multiple completes, and next the problem is remains same here, original problem, because here now in this s you need the number of a's, that is the multiple of 3. So one multiple completes, then problem remains same. So if you want to terminate, then you just write a here, or you if you have some more symbols, then you can go for the s. And here s can be the strings of only b's, or if s contains a, then it must be the multiple of 3. So say this is the grammar we have find for the given language. You need to verify whether all such derivation rules can generate the same language L4 or not. Means if this is the grammar is G for the L4, then your grammar G must be able to generate the language L4. And you can easily verify here. If you want to generate only B's, then you can follow these rules. And if you want to generate the multiple of A's, you can follow the rules like this. So here A and B can be in any order, we don't mind. Only we are going to control is that the number of A's must be the multiple of 3. That's all. So these are the rules for this grammars for this language. So see here, the language was looking some complex, and at the beginning it seems that okay, it is difficult to find out the grammar for this language, but having some properties and having some intuition for the originality of the problem. So always you need to say that what is the next part, whether the next part is the different problem or the next part is the same problem. So once the problem remains same, then you use the same non-terminals. So like here we have number of places we have seen. So here in the in this part, once you start from the B, then in this case you need to control the number of A's, and hence the original problem is what? Original problem is to control the number of A's, that must be the multiple of 3. So this is the original problem, that's why I have written S. Here once you have the A, here you have number of A's is in this, whatever the string you can generate starting from the symbol non-terminals A, whatever string you will generate by using these rules of the grammar, what you will find? Here you will find the x in which the number of a's is a multiple of 3. X contains the number of a's, a multiple of 3 minus 1. So here 1 less because you have used 1 here. So x contains the number of a's in x is a multiple of 3 minus 1. So number of a's in x is a multiple of 3 minus 1. So this non-terminal A is responsible for this kind of strings. And so once this non-terminals generates the string, you have one more A, and your original problem was number of A is a multiple of 3 is complete. So this you have to see. Now if A starts from the B, the problem remains same. Here if A starts with A, then problem change. Now you need 2 less number. Instead of 1 less, you need 2 less number of A's here. So that's why you need to find out, you have to remember that how many A's. Actually what you are going to do, you are going to remember that how many A's you have used up to this part, and that's why you are changing the non-terminals, and the problem is going to change. Once you have 2 A's you have used, the problem is different. So B, if B starts with B, then the problem remains same here. If B starts with A, then the problem completes. Now if you want more length, then again you will have the number of A's which is the multiple of 3, and this was the original problem, so you have written S. So using this kind of concept in any language, you will find very easy to find out the grammars, even the language looks complex. Okay, so this is the way you can use for finding the grammars. Now if somebody has given you some sentence of the language like B B A B A B B A. So if you are given the X double B A, then B A double B A, like this. This is the cent. The length of X is what? The length of X is 1, 2, 3, 4, 5, 6, 7, and 8. So you have the length of X is 8. Okay. Now, if somebody asks you that this is the grammar, you have the grammar, and you are given a grammar, and somebody gives you the grammar rules. Okay, this is the grammar, and I want to generate this sentence. Means you need to verify whether this X belongs to the language generated by the grammar G or not. So the question is that you may be given the problem like this. You will be given some grammars like here. I am going to give the grammar like this. And I ask that, okay, this is the sentence, and I want to verify whether this sentence can be generated by this grammar or not. Means you need to verify whatever the language represented by the grammar G we denote by writing LG. Means you need to verify whether X belongs to LG or not. And this is known as membership query. Membership query. So you have to answer the membership query. So how you can answer this membership query? Your input is a grammar and a sentence, and you will be asked whether this sentence can be generated by this grammar or not. So how can you find out? So again, the process is simple. What you need to do, you need to use the grammar rules for finding the sentence, for finding the string like this, and means you have to go for the derivation rules. Okay. So you need to find some derivations. So you have to start from the S. Then you need to see that which production rules I should apply. So for obtaining this, which production rules I should apply? Whether I should apply this, or this. So you have production rules 2, 4, 6, and 8. You have the 8 production rules. So your computer at the beginning, for the S, how many rules are there for the S? 1, 2, and 3. There are 3 rules. So out of 3, which rules should be applicable? Computer has to decide. And you know that your machine is not intelligent. Your computer is not intelligent. Like we are observing the grammar here, and we have the sentence here. You can easily see that since your sentence is beginning with B, so I have to start with the production rules like S derives BS. But how computer would know? So the only way for the computer is to go for the possible rules one by one. If it is going to apply one rules and it finds that, okay, I am not able to find out the strings, then it goes for the other possibilities. So if using the other possibility, is there any way to obtain the string? If no, then go for other possibilities. And if all possibilities exhaust and you are not going to find out the string this, then your computer will say that, okay, X is not in the language. So for the S, first time S, you have to find out of these 3 rules, computer has to find out of these 3 rules, which rules should be applicable. Once you apply, say for example, if you are going to apply S, if you are going for the rules S derives BS, then again you will have the difficulty which rules you need to apply out of 3. And if you have some in some way you are going to have the non-terminus a, then you have to think for the a whether you can apply for this rules or whether you can apply for this rules. So see the situations. If you if you have more number of rules, 100 rules, 200 rules, 500 rules, and you are given some string, and computer will find out the all possible combinations. So computer has to exercise all choices, and on exercising all choices, if there is no way to obtain the string, given string, then computer will say that okay, the given string or given sentence is not in the language. So see how difficult question is this. Even finding the membership query in computer science is a hard problem. So it's not easy job to obtain the membership query, because you might have for some complex grammar, you might have infinite possible derivation trees. Means actually whenever you are going to obtain the strings or sentence, then what you are going to do, you have to start from the s, and you are some observing some possible derivation trees. So you need to find out the derivation trees, and for complex grammar, for more number of rules, if you have more number of rules, then infinite possible derivation trees will be there. And computer has to test one by one all possible derivation trees. And on exploring all possible derivation trees, if it finds one derivation tree and it sees that okay, this is not able to generate the sentence, it goes for other derivation tree. If that derivation tree is also not able to generate the sentence, then it finds some other possible derivation trees, and so on. But for answering this query, whether X belongs to the language generated by the grammar or not, it has to exercise all possible derivation tree. It has to explore until it can't answer. So obtaining, exploring all possible, in worst case, if the language, in worst case, if sentence is not in the language, then your computer will your computer is busy with finding the derivation trees, and it is not able to obtain, and hence it becomes the intractable problems. And that's why even solving the membership query in some complex grammar, the grammar, the language, the grammar for the language, which are more expressive, it is very difficult to answer the membership queries. So even answering such kind of query is very difficult. So it's not an easy job. Next, if you are given some sentences, instead of listing all sentences, and if people has given some sentence and ask that okay, I have n sentences, okay, I have n sentences and I don't know what are the rules to obtain these sentences. Can you construct the grammar for these sentences? Then again, you need to find out the structure that can generate the n sentences. And also, if somebody tells you that this is some new sentences, then your grammar should, your learned grammar should also generate the new sentences. Then you can say that you have learned the grammars. So say this is also very challenging task. Learning efficient grammar for unknown language is a computationally hard problem in computer science.